Welcome back. We are going to look into poles and stability and see how poles can determine the stability of the system. Okay, so we are going to look into poles and stability. So, in order to do that, let's define a transfer function. Let's say that g of s is equal to s plus 5 divided by s plus 4 times the s plus 6. Okay, so now looking at this system, if you recall, this is the 4. If you recall, we said the system, when it goes to 0, that transfer function goes to 0, that is called the 0. So that can only happen if the numerator is equal to 0. So s plus 5 equals to 0, that means s is equal to minus 5, so there is going to be a 0 at s is equal to minus 5. Okay, so now we want to find the poles of the system. The way to do that is to make the transfer function go to infinity, and the only way to do that is to set the denominator equal to 0, and if you do that, that will be s plus 4 times the s plus 6. You are going to have two poles at minus 4 and at s is equal to minus 6. Let me call this poles. Okay. Now, if we do a pole 0 plot, you can see that both the poles are coming to the left-hand side of the plane, and hence you can conclude that the system indeed is going to be stable. So here, a rough plot, this is the real, and this is the imaginary. Okay, so you have a pole at minus 4, so 1, 2, 3, and minus 4, you got a pole right here. And also you have a 0, so we put a circle there, at minus 5, and then you have a pole at minus 6. Now both the poles are on the left hand side of the plane. So let me write this: left hand side of the plane, or left half of the plane. Left half of the plane. And since the poles are on the left half of the plane, you know that the system is going to be stable. The meaning is that when t goes to infinity, the transfer function of the system, especially the g of t in time domain, will go to 0. Well, let's see how we can do that. So here we have a transfer function, g of s, and we can find the inverse Laplace transform. First we got to apply that partial fractions. So let's take a look at that. So now it's going to be a over s plus 6 plus b over s plus 4, and we'll try to quickly do the partial fractions. The same math, we did it before, so we can do it again. So we can say that s plus 5 is equal to a times the s plus 4 plus b times the s plus 6. Okay, so if that's the case, we can get rid of the b by putting s is equal to minus 6. So let's do that. And if I put s is equal to minus 6 plus 4, then you will get a is equal to 1/2, right? So that's the math you can do. And suppose if we want to get rid of a, we put s is equal to minus 4. So let's try that out. So when s is equal to minus 4, this is that, and get rid of a, and that will be 2b, so b will be equal to half again. So here you go. You can write g of s in this format. You'll get half s plus 6 and plus the half s plus 4. Well, now we can take the inverse Laplace transform so that we can get this in time domain. So let's try to do that. We'll take the inverse of this, inverse Laplace transform this guy, inverse of this guy, and let's say we get a g of t is equal to half e to the power of minus 60 plus half e to the power of negative 40. And you can see the system is stable because as t goes to infinity, if we were to apply this limit t goes to infinity, then g of t will be indeed equal to 0, right? So let's do a little rough plot here of these two guys, and let's do the half over here. Let me do different colors, if you will. Let me do a black and a red. How about that? So if I do this e to the power of negative 40, it will eventually go like that, and that's your half point, and this is going to give you half e to the power of negative 40. Now notice this is going to be a little bit faster, so let me put this guy in red color. So this is going to go decay a little bit faster, and this is going to be half e to the power of minus 60. And of course, if you want to take the sum of the two, it's going to start somewhere at 1 and then decay down to. So the bottom line of this is, since both the poles are on the left hand side of the system, this system that we looked at is going to be stable. Now remember, we are just looking at the system response, the transfer function of the system. We are not putting the input to see the forced response and the natural response. Both of these guys, where you have e to the power of negative 40 and negative 60, these guys are also known as natural response of the system. So for the system to be stable, the natural response must go to 0 as t goes to infinity. So I'll see you shortly in the next video, where we are going to discuss the forced and the natural response together and see how that looks. Thank you.